So as you all guys know, water is very essential for us. However, the resources are very scarce, and what we have is very polluted. Not only because of agriculture or industrial stuff, but because of the pharmaceuticals and the organic stuff we manufacture ourselves, we synthesize. So what I'm mainly discussing is about pharmaceuticals, pesticides, and other trace organic compounds which are not removed by biological or conventional wastewater treatment systems. These are used in industrial agricultural stuff, uses, and they are extensively released in the environment. They are persistent because they're not biodegradable, they're not attacked, they cannot be attacked by microbes, and they're not affected by light and heat decomposition. So that's why we need to develop a new method that is able to remove them effectively and efficiently. So electrochemical advanced oxidation processes, when they employ such strong electrodes such as boron-doped diamond, they have this ability to remove such organic compounds because of two reasons. They have a high oxidation potential. We're talking about around 2.7 volt, which means if you can go up without producing oxygen, that's a very good merit. And that merit leads to another merit, which is the production of OH radicals, which are usually produced at a voltage around 2.8. So these two factors combined will lead to the removal of organic compounds at higher rates. However, hydroxyl radicals are not the only oxidizing agents in these systems. We would also have the effect of the electrolyte itself. So if we have a chloride-based electrolytes, these would produce a lot of oxidizing agents like chlorine, perchlorate. And also if we have sulfate, then there's another chance of having peroxydisulfate. However, in literature, most literature just assumes that sulfate is an inert electrolyte, does not react with the electrode, does not make any other stuff, just there for the conductivity and for the electron transfer. And they ignore that S2O8 is being produced, so they just say it's mentioned, but they don't really study the contribution of that system, of that compound to the system. So in case we have a system of electrochemical advanced oxidation process with a BDD and sulfate, we can't only account for the OH radicals. We have to also account for the S2O8 being produced. So the question is, does the formed S2O8 play a role in the oxidation? That is something I will try to prove. But in which form? Is it S2O8 itself? Because that is an oxidizing agent. It's strong, but it might be a bit slow. So is that fast or is that slow? What's going on? And when we prove this, we need to account for the oxidation kinetics. So if we have OH and SO4, which one is doing how much of the work? Recent research in our lab suggests that SO4 radicals are being produced in such a system, and that would certainly contribute to the oxidation besides the OH radicals. So the formation of S2O8 on BDD is not agreed upon in literature. Some claim that it's a direct oxidation. You put SO4 with the BDD, you get S2O8. Some claim that there is a role of the radicals themselves. So SO4 radical is being produced from OH radicals, and then these radicals combine to form S2O8. Other guys just go too complicated and they assume something adsorbed on something, OH adsorbed on the BDD, and then that reacts with sulfate to form adsorbed sulfate radical, which reacts with sulfate ion to produce S2O8. None of this has been just said confidently that one works and the other doesn't work. So we'll try to just to give some evidence to explain which one is more likely than the other one to happen. In our system, I have an electrochemical system divided with a cation exchange membrane. The BDD is the anode, stainless steel is the cathode. In my anolyte, I use sulfate ions and I compare it to another inert. That one is confirmed as inert nitrate. I use it in both of them with the same conductivity, but I inject my 15 organic compounds in the anolyte. So I have 15 organic compounds, each with 2 micromolar. I use an anodic potential of 3.4, so I want it higher than 2.8, which is for hydroxyl radicals. I don't do any pH control, so I leave it in the acidic media itself, flow rate of 200 milliliter per minute. So my hypothesis is in SO4 electrolyte, I would be having both radicals, while in NO3 I would be having only OH radicals. So this would mean that I am expecting a higher removal in SO4 2- electrolyte. So our preliminary results show that SO4 is not only higher, but it's even 10 times faster than NO3. it can remove tribromophene or isopromide 10 times, and sometimes in less than 1 hour compared to 8 hours in NO3. However, this 10 times factor is not in all chemicals, so it also depends on the chemical structural formula, what kind of substitute functional groups on the aromatic ring. But what we could see that SO4 in 2 hours can remove much faster than what NO3 can remove in 8 hours. This factor goes 10 times here, but sometimes goes to 3 or 4 times in other chemicals. I did a further experiment, but without using any organics. I said, okay, let's just put SO4 2- on a BDD and measure S208. But I had to choose the right potential. So I compared, because S208 is not expected to show up before below 2.1, and I don't have OH radicals below 2.8. So I said, I'll try one system above 2.8, where I'll be having both of them, and I'll try one below 2.8 but higher than 2.1, and that will remove the factor of OH radicals. So the results show that in the case where I have SO4 with a high potential, S208 is being produced linearly with a concentration of up to 1.2 millimolar after 6 hours. While if I have it at a low potential of 2.25, I don't have any S208 being produced. So that emphasizes the role of the OH radical being active in the production of S208 as well as sulfate radicals, because as I said before, it's either direct oxidation or a combination of radicals. When I put S208 only by itself with a high potential on the electrode, nothing happened. So this means S208 itself is a very stable thing. I did some cyclic voltammetry results just to see if there is a reaction and when is it happening. And when I put H2SO4, I could see a very small peak. That one won't be appearing here because we have a very high oxidation potential and high production of oxygen. But if you make a very strong zoom in on this figure, you'll observe a very small peak. And that's not only with a very low as H2SO4. With Na2SO4 it also appears, but the peak is a bit shifted. So the pH would play a role in this reaction and the production of S208. And when I did the cyclic voltammetry for S208, I didn't observe anything. There's no peak around that. So this means that S208 is being formed, but it's being a bit stable afterwards. So the explanation to this is that S208 is being formed, and in its formation mechanism, OH radical is playing a role, and SO4 radical is playing as well a role, but before the formation of S208. So SO4 is formed, then S208 is formed. And when SO4 is formed, it's playing a role in the organic removal or oxidation. And then because it's a catalyst, it doesn't react, it doesn't go like OH on the system sometimes, or on the aromatic ring. So it's being just reacting with itself again to form S208. So just to wrap up what I was talking about, we observed a fast oxidation when we were using SO4 electrolyte, which proves that it's not an inert electrolyte, on the contrary of what's published in literature, and that suggests or gives us more evidence about the formation of SO4 radicals. The formation of S208 in such a system of combined BDD and SO4 2- shows that OH radicals are not the only oxidants, and the additional peak, what we saw in the cyclic voltammetry, provides additional evidence for that thing. On the long level, the pH, flow rate, and the potential will be optimized to make use or make benefit of the presence of these two radicals by doing some kind of competition or kinetic competition between these two radicals to see what's the best optimized way. And the main application for this method or for this technique is what Guillermo was presenting a bit before, which is mining, where we have a lot of sulfate, which we don't know what to do with it. So we can not remove it, but we can use it in order to remove other organics from other systems. So we're combining two waste water systems to have a cleaner system with a good yield, as I can say. So thank you, and I'll be happy to answer any kind of questions. Yes.
So in your study, you have selected many chemical compounds as a target. So did you detect the final products or the byproducts in your system?
No, I didn't work on the byproducts because I wanted to make sure that the experiment is first removing these organics, and the second stage would be I'm focusing on one chemical just because it's very resistant, and I'll be studying its byproduct and where it's going.
So you were studying the transformation of the 10 compounds.
Yeah, but I cannot choose. I can't work on the 15 compounds. That's a lot. So I just choose like 3 or 4 of them, which are not removed with other compound or other techniques to focus on. Since I was explaining, yeah.
So can you just go back to the last thing you said about the intention of utilizing this for the mining industry? Is it taking the sulfate radicals, the excess of sulfate that you have, and then making it into radicals that are very active for treatment of something else?
Yeah.
On site?
Well, the technique we were thinking of is electrodialysis. So I think that's what hit our head first, that we use electrodialysis as an electrochemical system to remove sulfate from that water and then use it in another system. So it's like a combined system of both. To what extent we can remove it on site, I mean, I'm not sure. That depends on the work itself, because even one of the things I need to work on is how low I can go with sulfate concentration, because I use 50 millimolar, which is a bit high. It's around 7,000 milligrams per liter. But if I can go down to, let's say, 50 milligrams per liter, that is what's already present in drinking water sometimes. So I can just get the water itself if I want. I'm not needing to add any sulfate, and I can just treat it this way.
So the radicals are metastatic. Like they're short-lived in a way, right? So you make this product, which is really, really good, highly reactive, and it treats very well, but it only lasts for a little while.
Yeah.
If you're in a mine in the middle of Australia, in the center, what do you do with it?
So, I mean, because you have treatment plants for the mining, I mean, usually you just release it in the river, because they have like industrial rivers that can go up to the treatment plant. So I would be waiting for the mining water to come to my treatment plant. If that answers the question.
Okay, thanks.
Thank you, guys.